So we made the point that we've talked about these separate systems, flow, transport, and of contaminants of mass and also of heat, and also of momentum transport, if you like, although we're using it really only in the steady state case for solid mechanics. We've made this distinction between the flow problems, which are really only for scalar values, concentration, pressure or head, concentration or temperature, and those which involve vectoral quantities such as displacements and forces for solid mechanics. And then we made the point that in each of these systems, we're either using a constitutive model, which is either Darcy's law or Fick's law or Fourier's law or Hooke's law for each of them. But no matter which ones we use, we end up with a system of equations, and if we use that system of equations, they all populate the leading diagonals of these kind of global matrices. And if we do that, there's no linkage between them. And if we want the different systems to interact in some way, then we have to be able to have these off-diagonal coupling matrices. And so I think we went through in reasonable detail to say at least what some of those would be. So what I plan to do today is to do what I was going to do last time. I guess it was an impromptu change. It just happened. Whereas we were going to talk about dual porosity, dual permeability systems, which are kind of a coupling system, but not in the way that we define this, because the coupling is between two flow systems, as we'll see. And then after that, we'll talk about coupling hydromechanical behavior, which we said a little bit about last time, and work through that, and then work through successively more involved couplings, and then talk about how we might do that coupling in a variety of different ways. Purpose-built codes to do it, or leapfrogging between individual codes that might do solid mechanics separately and fluid mechanics separately, and having them parse between them the appropriate information to be able to make them talk to each other and to be able to do some things. And so what I wanted to do today was talk about the first of the linked mechanisms, and the first one that we'll talk about would be dual porosity, dual permeability systems. And I suppose one way to do that would be just to draw something instead of actually. So let me fill this to the whole system. So if I start off on this, so dual permeability and dual porosity systems. They're slightly different. And it's to merely take care of fractured rocks. And so fractured rocks, you could imagine that if you look at an outcrop of a rock, if you drive down, well, some of you are geologists, of course, and some are not. But if you drive down 322 and look at the limestone cuts, you'll see rocks which have fractures which separate or bound matrix blocks. So the matrix blocks typically have, and I'm trying to think what the terminology we use. We use a conductivity for the matrix and a storage for the matrix. And you'll recall that when we talk about flow in these systems, we have an expression that is something like the second order partial differential equation. If we just write it in one dimension, looks something like this. So the transport term that includes Darcy's law, and the capacitance term that includes the time taken to deplete a certain volume from the matrix. And so the characteristics of fractured rocks has been realized for certainly more than 50 or 60 years now, that fractures and matrix serve two different purposes. So if you look at an oil reservoir, or a groundwater reservoir for that matter, all of the storage, all of the volume of fluid is present within the large volume of matrix blocks with a relatively large porosity, maybe of 25, 30%. And so all the volume of fluid that exists within that either aquifer or reservoir exists because of the storage is relatively large, and the volume of it as well. If you look at the proportion to the volumes of fractures to matrix, then almost all of it is matrix. The fractures might be, say, probably less than 1% of the total volume. But the fractures provide an essential behavior, or the fracture network, and they have some hydraulic conductivity attached to them and some storage attached to them. And so if we thought of the matrix blocks as being completely impermeable, then we could write an equation that describes this, which would be something like this. Just writing the first term, it could be x, y, and z with three dimensions as well. And in this particular case, the attributes of the fractures are that they're really very permeable. All the fluid that seeps out of this thing will come out through the fractures, but they have no storage. So the fractures will respond very quickly. So you put a straw in and you suck some fluid out of here. The fractures will respond very quickly. The matrix blocks will respond much more slowly, but be conditioned by basically the model that we would look at would be something like individual spherical blocks you could imagine that somehow flow fluid into these fractures that surround it in response to the changing fluid pressure or changing head within these fractures. And so the fact that they have intrinsically different behaviors, high permeability in the fracture network, high storage in the matrix blocks, and conversely low permeability in the matrix and low storage in the fractures, means that they behave in two different ways. And so if we thought about them individually, you could imagine that if the matrix blocks were impermeable, then it would only be the permeability of the fracture network which would contribute to flow. And so when we talk about this permeability, and I think it's important to realize this, that both Kf and Km are equivalent permeabilities or conductivities, equivalent conductivities of fracture and matrix, fracture network and matrix, respectively. And so the easiest way, I think, to think about that is, so this permeability, say, of K fractures would be basically this little cameo that we have here, where you did a little experiment on a sample, and say you had maybe we should draw it actually as a core. So you did an experiment on a core that included this, and you had a head upstream, you had a head downstream, and you used Darcy's law to calculate a flow rate as a function of cross-sectional area of the sample and hydraulic conductivity and the change in head with length. This is length. This is L. So this would go in here. And so this would be the flow within the fracture, I guess, fracture network we said. So it requires that basically you make the matrix blocks impermeable. And so that would mean then that if you had a fracture network that looked like in a block, say the fracture network looked like this, that the permeability of the fracture network in this case would be 0, right? Because it's not connected. There's a gap here which it can't get through. And so if we're saying that the matrix block Km in this case goes to 0, and we want to calculate what the fracture network permeability is, in the case where this is not connected, it's below, as people would call it, below the percolation threshold. It can't percolate because it's not connected from one side to the other. The permeability would be 0. If we were to connect it by doing this, then all of a sudden it would have some finite value, and we could calculate what that is. But the point is that this permeability that we're using isn't the permeability of individual fractures, but it's the bulk permeability of the fracture network when the other medium is turned off to 0. Likewise, we could do that for the matrix, and we could just repeat it for the matrix. I won't do this diagram again, but if we did it for the matrix, then the equivalent behavior would be true. And that is that we would take this, and if we add a fracture network to this, then with the fractures set to 0, Kf equals 0, so nothing can go across them. So now in this particular case, I guess this would have some permeability because you can imagine something flowing from one side to the other. If you complete this network and do this, then all of a sudden the permeability of the matrix now would be 0. And so the point that we're trying to make is that these values are kind of geometric. They're not just the individual permeability of a piece of matrix or a piece of fracture, but they're the hydraulic conductivity of the system per se. So that's the first part. And so you could imagine that if we looked at either of these systems individually, we thought of it as all comprising matrix, we could solve this equation. If we thought of it as all comprising fractures with the other component turned off, we would have the behavior of the fracture system. But what we'd like to do is be able to represent the behavior of the two systems together. And so our way of doing that is to think of it as what we sometimes referred to as overlapping continua. Is it two P's in lapping? I can't remember. Is it two P's? And so that is that we look at a system where, for instance, if we took the behavior, so I'll draw a simpler diagram of this. So if we imagine a system that looks like this, where we have fractures, and this is in our little contour outside it. So now, if we, for instance, plotted the change in fluid pressure with location as we went through here as one section, A prime, or whatever you want to call it, then these are the locations of our fractures. And so you could imagine that if we plot either pressure or head, I guess we've used in this, imagine that we have something that starts off like this. The pressures are uniform in both the porous medium and the fractures. What would happen if we, for instance, all of a sudden drew down this by changing the head at this particular location or pulling some fluid out? Then the fractures would respond very quickly. And so, actually, this is probably a good place to use colors. And so the fracture pressures might respond very quickly by being drawn down by some amount here. And it could be the same in both ones, or one could actually be lower than the other one. But because the permeability of the matrix material inside this is very low, then initially the pressures in the matrix would give a profile that looks like the one I'm drawing here. Fractures pressures heads go down, but the matrix remains constant. So this would be t equals 0 plus. I guess the red would be t equals 0 minus, the instant before we turn the boundary condition on. And I suppose t at successive behaviors would start looking like, not drawing it very well, down to some boundary condition that I guess it has to be, no, that could be right, yeah. It would be something that's drawn down here. And at time infinity, it would look something like this, as a straight line. So this is t equals infinity, and this would be t1, sometime between them. And so what's physically happening, if I blow that up a little bit, is that it's responding to the fractures first, and then the matrix is being drawn down in response to it. The ultimate behavior is some kind of steady behavior, which is a new baseline, which has a no release of storage from the matrix into the fractures. This is releasing into the fractures. If you look, for instance, here at this gradient, this is delta H, and this is delta X. Bit blunt there. And so you can know from this gradient that it has to be flowing out of the matrix towards to your left, I guess. It's on your left as well, and into the fractures. And so this is the real response that we want to represent. And we want to try and represent it through this behavior that we have here. But we've defined two individual expressions. And so the one thing I haven't done within these expressions is that we could think about this in terms of the hydraulic conductivity of the matrix and the storage of the matrix. And of course, there is only one value of head. But we could think of this head as being the head that exists within the matrix. This one. And we could think about this equation here as the head that exists within the fractures. And so if we do that, then all of a sudden, clearly, there is only one value of head. It can only, wherever you are located, there's one pressure that you could measure because there's one fluid that's in the system, and therefore it's a fluid pressure. But we're going to make the assumption that we can actually divide them into two separate systems. And separate systems allow us to be able to look at the head within the fractures, which would only exist here. So in other words, here would be the head within the fracture, and here would be the head within the fracture. And if I use a different color, everywhere else up to that point would be head within the matrix, etc. Even though we've said that that's completely an aberration that is, because there's a head, there's a fluid, and it has a pressure. It happens to be in a matrix or the fracture, it doesn't really matter, it still just has a pressure. And so our reason for doing that is that we can think about these systems individually, and we could look at the behavior only of the fractures, the behavior only of the matrix, and then find some way to link the two so they can talk to each other. And that's essentially what we would do. And so the easiest way to think about doing that would be to take these expressions that we had earlier on, which is a hydraulic conductivity within the matrix, a change in head within the matrix, being equal to the storage within the matrix, and again the head within the matrix with time, and the converse for the fracture system. And to realize that the units of this, if we look at the units of this and understand what it means, is the units of this, I think, are a mass per unit a mass flux per unit volume. So let's look at this. So hydraulic conductivity is meters per second. This is meters, head is meters, and this is over meters squared. And so the units of this are rather strange units of 1 over seconds. But you could also write 1 over seconds as meters cubed per second per meter, right? Meter cubed, rather. So all I've done is multiply top and bottom by meter cubed. And so this is saying this is a volumetric flow rate that's occurring per unit volume of the aquifer or reservoir. And so all of the terms, since we're adding apples to apples, all have to be written in terms of this 1 over seconds unit, but it's really a volumetric flow rate per unit volume. That's really what it is. And so what we could do is we could think of this, and actually as we've written this expression before, we could write this in terms of some volumetric distributed flux over here. And so what we could do, if we wanted to make them talk to each other, we could take, and physically we've made this point that what's happening is that if we draw down the fluid heads or pressures within the fracture, it's going to flow out of the matrix into the fracture. Then there has to be a mass balance between whatever goes out of the matrix has to be the same volumetric flow rate that goes into the fracture. And so quite simply, we could write it as plus Q and minus Q, where this is basically a transfer term. And so we have to think how we could be able to represent that. And the easiest way to think about it, I would say, is if you take if you do Darcy's law. And so you take a block, and this block might be the matrix block that's surrounded by 4 fractures in this case. And we simplify this block to make it look like something that would have a head within the matrix at the central portion, and at all other parts around it, it would have a head within the fracture, which we'll call H sub f. And you could then redraw this in some way. I guess you could draw it like this. As HF, I'm just going to take a portion which is this. And this is sorry, that's not HF, is it? At all. I guess I have to use this. Oh, didn't quite mean to do that. It's matrix, right? This is HM, and this is HF, which is also, you could think of it as like, I'm running out of space here, basic Darcy's law. Upstream is HM, and downstream is HF. And so the interest in doing this is it allows us to write a so-called steady state approximation of what this transfer term would be. And so you could imagine that this transfer term should be something like HM minus HF multiplied by some factor, which I think we'll use pi later on. And this would be equal to HM minus HF multiplied by the same factor. So it's basically writing Darcy's law, because Q in this case would be equal to some hydraulic conductivity, some area, HM minus HF, divided by whatever this length is. That's all. And that's it. And so having some rational way of being able to do this is to do this. And of course, the interest in writing it in terms of these heads is that these are the only dependent variables we have here. And so that's basically the way that dual permeability or dual porosity models have developed. So this, if you want references for this, so these are from, So Warren and Root, they developed independently. Warren and Root in the US, I think 1963. And Barenblatt and others, et al., the literature grew up in Russia, and I think it was early 1960s also. I don't know. Or might have been 1950s, but certainly the West and the East weren't talking very much in those days. I guess we've kind of reverted a little bit back to that, but anyway. So that's the genesis of dual porosity models. So these are dual porosity models. And I'll just explain. And so the difference between, we made this point of defining both dual porosity and dual permeability systems as before. And so there's a slight difference to it in terms of what they mean. So dual porosity systems are basically systems where we consider that, actually might be worthwhile writing it out, that Km goes to 0. And also, typically, the storage in the fractures is also ignored. And so, in other words, it includes only flow that occurs from the center of this block into the fracture and then out. Dual permeability systems include the case where the matrix permeability is not equal to 0. And it may, or I think I won't complicate it by talking about the storage. And so that means that, for instance, in the dual permeability system, then if you have a finite permeability in the matrix, then it can flow in two modes. It can flow in steady state through the matrix to this point, but it also can flow from these individual blocks into the fractures. So there's two modes which it can flow. In the dual porosity system, it can only flow from here into the fractures and not across it. And so I suppose the subtle difference would be that in steady state, in other words, when you reach this green line at the bottom here, by definition in the dual porosity system, since the flow has to come from the block into the fracture, and at steady state that is now all depleted because it's not transient anymore, then the only flow in the system is through the fractures from one side to the other. But in a dual permeability system, once it's depleted from the storage is depleted from the blocks into the fractures, it can still flow across the system through the blocks in addition to flow through the fractures. So it's maybe a small difference between them, but they are different. Functionally, it doesn't make much difference to the outcomes. I'm not sure I was doing that. Let's try and make this smaller. Yeah. Okay. So those are dual permeability systems. So you can probably see from this that since the two systems that we're representing, we're attempting to represent in each of these systems of equations, and we know exactly how to write a second order PDE as a finite element equation, and we know exactly how to write a zeroth order expression for permeability equation, and we know that we also have a term that is something like HF minus HM running out of space here, and minus some term times HF minus HM, then we have to figure out how to deal with this. And of course, this doesn't change with time. So when we say zeroth order in space and first order in time, that represents this derivative. This is zeroth order in space, and this is zeroth order in time. And we know how to do that. We know exactly what that matrix equation would look like. And so to go back to what I was going to start off doing, I guess I want to do this. We'll just resume where we are here. We've talked about the concepts. We're going to talk about dual permeability, and we're going to do it just heuristically. based on how we might solve the system of equations. So this should start looking maybe familiar to you as we go through this. So we'll talk about how we derive the finite element equations. It's pretty straightforward. This is the expression we have here. We've made the case that fractures have high permeability and low storage, and the matrix has high storage and low hydraulic conductivity. This would be the expression we have for 2 dimensions from this left-hand side. I think in this case we're using the porous, so this is the porous medium here. And this is the fracture network. And so this is what we had called before Km and Kf, etc. But so I think it's pretty transparent. So we're just using 1s and 2s instead of the m's and f's. This is the storage term within the porous medium, storage within the fractures, and this is A is the size of the individual blocks. So it's a length scale. So this is A. And pi is some leak-off parameter, leakage parameter or leak-off parameter. And you can get it from Warren and Root's papers or Barenblatt's papers. It's just based on dimensional analysis, but basically based on applying Darcy's law. And so what we know about these are, this is a second order, this is 0th order, first in time, this is 0th order, 0th in time. And so what we can do is we can write these as finite element equations, and we know they'd look like this. Written for the porous medium here, written for the fracture. This you'll recognize operating on rate of change of head. And this may be new, but we know what is this matrix going to look like if we write it out in finite element form. It's 0th order in space, and so we know for that 0th order in space is basically our storage matrix, what we've called S, which is equal to B transposed B dV over the volume. These are the shape functions. We know that if we add up all the terms within this matrix relationship, we end up with the volume of the element. That's what it represents. And so that is what we're going to use here. This is basically going to be our B matrix is going to be what? It's going to be equal to this term here. I'll leave a little space. B transposed B dV. And it's pre-multiplied by pi a squared. Nothing more than that. That's our parameter that does this. So this is our storage term. This isn't the matrix. So, okay, perhaps that's worthwhile making that observation. This S1 and this S1 are not the same, right? This is the matrix relationship, so this S1 here would be B transpose B dV integral multiplied by S1. Just in case there's any doubt. And so this is a matrix that operates on the heads here, and they're just subtracted from each other. This is the finite element representation of nodal fluxes. We can write it for the matrix. We can write it for the fractures. And we can note that it's true at any particular time we write it, which is what tau is. And I guess this is right. I guess I didn't really need to write that out because it's written right here. And so we can choose implicit or explicit ways of solving it. And if we choose implicit, we just write it at tau equals t plus delta t. Right? You'll remember that we talk about the changes in heads occurring over time t and t plus delta t. And we have something that looks like this. Head at time t, head at time t plus delta t. Not very good handwriting, but you got it. And these equations are exact at that time, and we just have to define what the time derivative is, which is just equal to the change in head divided by the time step over which it occurs, which is basically delta H over delta T. So you remember that. And so if we substitute this value here into here and into, whoops, here, then we can rewrite the expressions as at the bottom of the page, or the top of the new page, where we have added this. We've made the point that we know these values at the time step t plus delta t, which is what's written here. And we can start rearranging it for the things that we know and the things we don't know. The things that we know would be the heads at time t. So that's what we know. The things that we'd like to know would be the heads at time t plus delta t. And so if we make that those changes, then we can take this over to the left-hand side. We can take this over to the left-hand side. Sorry, right-hand side, which by pre-multiplying by this. And so those are those terms that we have here. And the rest of it all gets condensed into dealing with, it's either dealing with the head within the matrix at time t plus delta t, or the head within the fracture at time t plus delta t. And so those that exist, these two things within this vector here. And that's true for the other equation. And so if you just compress this or concatenate this into this matrix relationship, then these are the individual matrix relations we have. The term on the diagonal is going to include this term, all the terms that operate on H1, which are this, this has gone to the other side, and this. So hence, if we add these three together, we end up with the conductance matrix, the time-dependent part, and the B matrix, which will go on the diagonal. It's exactly the same. The terms that then operate on H2 are going to be the only ones that are remaining, which I guess is this one. And so that would be this term here, which is just B. B operates on that. And so this is the term that goes in there, which goes here. And if you look at the one for, if this one is for the matrix and this one is for the fractures, then the magnitudes of these that come out would be, this starts looking the same. So we gather the terms that operate on H2, which would be the ones that go in here. And it would be this term. It would be this term. This one's already scooted across, and it would be these two terms together, right? And so the expression for A2 looks like it just by transposing the index, the scripts, the subscript, is 2. And if you look at the remaining term for the interaction, then it's this one here, operating on this. And so clearly this is just B as well. So the matrix actually is symmetric. We know that by definition, yeah, that's an interesting point. We know by definition that K1 is equal to what? It's equal to A transpose D A dV. And by definition, because D is symmetric, it's Darcy's law, and because A are not symmetric individually, but when you multiply a transpose with the other one, they come out to be symmetric, then K is symmetric. S1 is symmetric, and we'd only compress it down onto the leading diagonal. And B is a matrix that's just like S1 as well. It's also symmetric. So A1 on its own is symmetric. So this is symmetric. A2 by definition is symmetric. And A3 is symmetric. And this actually would be kind of the transpose of it. So that the point I'm trying to make is that this whole matrix relationship here remains a symmetric system of equations. And it's relatively straightforward to solve as a result. I guess we've never really gone into it in any detail, but most finite element codes take because they are symmetric, they take a matrix and they would typically save only the parts that exist including and above the leading diagonal. So they don't bother keeping the stuff here because they know it's a mirror image of the stuff above it. And so all the computations that are done, first of all, you have smaller storage because you don't have to store everything below it. And secondly, the computations that you do in terms of multiplying for these ones, you can do more economically because you don't actually, you can do the multiplications which you have to do in solving the matrix by proxy, basically, without doing them. So that's it, I think. So that's dual porosity models and dual permeability models. And so then it comes down to merely how you'd implement this. And so you could implement it in a couple of different ways, I guess. I guess we could do, if we wanted to, we could put it in EGE-FEM because you have the matrix relationships for it. And it would certainly solve for that. I've never done that, but I think it'd be a pretty straightforward task to do. And the other way we could do it is try using CumSol.